Hello everyone, I am Kirti. Today we shall cover field gradient pulses and diffusion ordered spectroscopy. So this field gradient pulses and diffusion ordered spectroscopy, they come under advanced NMR spectroscopy. So in this lecture, we shall see what are field gradient pulses and how can we use these field gradient pulses to perform DOSI experiments in NMR. By the way, this DOSI, it is an acronym for diffusion ordered spectroscopy. So using this DOSI experiments, one can find the diffusion coefficients of the molecules in a particular medium. That is, how fast or how slow your molecules are moving in a particular medium. That can be found using DOSI. So this DOSI, it also has numerous applications in different areas of chemistry, particularly in research, about which we shall see at the end of this presentation. But before we move forward to understand this field gradient pulses, we need to have the basic understanding of the hardware of NMR spectrometer. If not much, we should at least know about two things. That is, what is an NMR magnet and what is an NMR probe. So we know that NMR spectrometers, they are always associated with certain frequency, like we call a 200 megahertz spectrometer or a 300 megahertz spectrometer. So this frequency is the frequency of the magnetic field which is generated by the magnet which is present in the NMR spectrometer. So every NMR spectrometer has a magnet present inside it. Okay. So that magnet is nothing but it is a coil, right? It is in the form of a coil, and this coil, it is placed in the reservoir of liquid helium. Okay. Basically, these coils are made up of niobium titanium or niobium tin alloys. So whenever a metal coil is placed in a liquid helium, we know that this liquid helium is at a temperature of 4 Kelvin, right? 4 Kelvin. So wherever any metal coil is placed at such low temperature, then this metal coil, it acts as a superconductor. So whenever you pass a current in this coil, it will generate a magnetic field. So whenever you pass a current in this coil, it will generate magnetic field of very high field strength in the direction perpendicular to the direction of the plane of the coil. Okay, so if your coil is like this, so your magnetic field will be directed in a perpendicular direction. So this magnetic field will be of very high field strength, right? Because this coil, it is a superconductor, so the magnetic field generated by this coil will have a high field strength. So this magnetic field is called an external magnetic field, and it is represented by B naught. Okay, I'm sorry. So it is this magnetic field which is this magnetic field which is generated by the magnet present in NMR is called external magnetic field, and it is represented by B naught. So yeah, let us see what is an NMR probe. So this NMR probe is a structure which sits in the bore of this NMR magnet. So this NMR magnet has a hole or bore. Inside this bore, this NMR probe goes and sits. Okay. So this NMR probe, it also has so many, this coil kind of things wrapped around it or bound around it. So what are those coils? Those are RF coils, shim coils, and gradient coils. Let us see or look at the function of these coils one by one. So this RF coils, they are used to send RF frequency to the sample. Okay, so these using these coils, we can pass the radio frequency to excite your sample. And the same coils are used to receive the signals from the sample. So now let us see what are shim coils. We know that a magnetic field generated by the magnet present inside this NMR is B naught, right? It's a very high field strength. But this B naught is not constant with time. It always keeps drifting, okay? Suppose your B naught is 200 megahertz. So, with time, excuse me, with time, this field is not constant. it will be at least 200 megahertz plus 8 to 10 hertz, or 200 megahertz minus minus 8 to 10 hertz. Okay. So this field drift or field shift of 8 to 10 hertz is very small when compared to 200 megahertz, but it might affect your signals. Okay. So this inhomogeneity in field has to be nullified or reduced. Okay. So that we can do using this shim coils. So this shim coils, they are used to homogenize the magnetic field which is experienced by the sample. Okay, at some region you might, due to this drift in the magnetic field, at some region the molecules might experience 200 megahertz plus 8 hertz field, and at some other region they might experience 200 megahertz minus 8 hertz. Okay, so this field homogeneity is obtained by passing small currents in the string coils. So these currents will compensate for the drifts in the magnetic field. So this technique is called shimming. Okay. So by performing this shimming, one can ensure that the magnetic field is homogeneous throughout your sample. So this is your magnet. Inside the bore of the magnet, there is an NMR probe. So inside this probe, you have your sample. Okay. So this probe has this RF string coils and gradient coils wrapped around it. So let us see what are gradient coils. This gradient coils are those coils to which we pass the gradient pulses. Okay, so let us learn about these coils in detail. So the gradient coils are two circular coils. They are placed one above and one below this RF coil. Okay, so when you pass a current through this gradient coil in this anti-clockwise direction, according to this right hand thumb rule, it generates a magnetic field in this direction perpendicular to the plane of this coil. So when you pass a current through this coil in opposite direction, like in this clockwise direction, you generate a magnetic field, or I mean this coil generates a magnetic field which is perpendicular to the plane of this coil in downward direction. Okay. So when you place your sample inside the NMR spectrometer, this sample, it will experience the external magnetic field which is B naught. Okay, it experiences this B naught magnetic field, and this magnetic field is homogeneous throughout this sample. Okay, throughout this sample, this field is homogeneous because we have performed the shimming. Okay, so when you pass the current through this gradient coil, what happens? Now this coil generates a magnetic field in this direction, and this coil generates a magnetic field in downward direction. Now when you look at the molecules which are present in this region near to this upper coil, in addition to the field B naught, they will experience the field B. Okay. So the net field experienced by the molecules in this region will be B naught plus B. Since both the fields have the same direction. So B naught is also directed in this direction along Z axis, and B is also directed along Z axis. Now when you look at the molecules in this region near this lower coil, the molecules in this region will experience a magnetic field which is less than B naught, because the magnetic field generated by this coil points in the opposite direction of B naught. So the net magnetic field experienced by the molecules in this region will be B naught minus B. Now as you move down from this region, the effect of this positive magnetic field decreases, and at some point it becomes 0. Okay, this B becomes 0. As you move upward from this coil in this direction, as you move in this direction, the effect of this negative field decreases, and this negative field at some point it becomes 0. So at the center of this these two coils, the field experienced by the molecules will be B naught. That is only the external magnetic field is experienced by the molecules at the center. Now, if you think of this uh, whole sample, you can think of it as a series of small regions or small chunks. Okay, so this sample, you can think of it as a series of small chunks or slices, and the molecules in each slice will experience a different magnetic field. See, at the center, the magnetic field was V naught, but as you move up, the effect of positive magnetic field increases. And the field becomes V naught plus X, then V naught plus 2X, and at the top, the field will be highest, that is V naught plus 3X. But as you move down from V naught, the effect of this negative field increases. So the field here will be V naught minus X. Here, the V naught minus 2X. As you move down near to the coil, the negative will be highest, that will be V naught minus 3x. So this x and x is an arbitrary number. Okay. So we know that the Larmor precision frequency, that is the frequency with which the magnetization vector rotates around the RF pulse, that is V1. So that is called Larmor precision frequency. This precision frequency is equal to gamma into V naught, where gamma is the gyromagnetic ratio and V naught is the field experienced by the molecules. But we know that molecules in different regions are now experiencing different fields. So the molecules the magnetization vectors of the molecules will persist at different frequency in this different regions, right? If you look at a particular proton, the magnetization vector of a particular proton, and in this region, look here, this is the magnetization vector of a particular proton. At the center, the magnetization vector, it processes with the frequency of gamma into V naught. But move upwards, as you move upwards, the precisional frequency of this magnetization vector increases. Since the precisional frequency depends upon the magnetic field experienced by the magnetization vectors, as the magnetic field increases in this direction, the precisional frequency also increases. So this vector rotates faster than this vector by an angle theta. Okay. Hmm. So this vector is rotating faster than this vector. So by an angle theta. So as you move up, the value of this theta increases. Okay. Now when you look at this vectors which are placed in this direction, which are below this V naught. So these vectors will rotate slower than the magnetization vector which is present in this region. So this will rotate slower by an angle theta. So as you move down, the value of theta increases in opposite direction. So if you look at the magnetization vectors, or if you look at this sample, sorry, so if you look at this sample in this direction, if you have a top view of this sample, you will see something like this. So these magnetization vectors, they appear to be defaced in this plane. Okay. Suppose if this is an XY plane, so these magnetization vectors appear to be defaced. Now let me tell you an important thing. The intensity of the signal, it depends upon this intensity, it depends upon the sum of the magnetization vectors. Okay. So that depends upon the net magnetization vector, or I can call magnitude of net magnetization vector. But when you sum these magnetization vectors, what happens? This vector will be cancelled by this vector, since their magnitude is equal but they are in opposite direction. So all the vectors, they cancel each other. So the net sum will become 0. So the intensity of this peak will be 0. That means the peak intensity it becomes minimum, right? The peak dies. Okay. So by applying a gradient, by applying a gradient field, you can see that the intensity of the signal decreased to 0. Okay, then it will be of no use, right? Now I want to get back my signal. So how do I do that? So for that, I need to bring back these magnetization vectors in the same direction. Okay, so all the magnetization vectors should persist with the same frequency. Now how can I do that? Let us see. So in the presence of only V naught, when we did not apply any gradient, all the magnetization vectors of a particular proton type, they were processing with the same frequency. Okay, so all they were aligned. Even at different times, all the magnetization vectors were aligned and the signal intensity was maximum. But when you applied a gradient, the magnetization vectors, they started processing with different frequency. So all the magnetization vectors, they dephased in the xy plane. For this reason, the net magnetization vector became 0 and the magnitude of net magnetization vector became 0. So the signal did not have any intensity. Okay. Now I can get back this condition by applying a reverse gradient. Okay. So then I apply a reverse gradient in this direction of same strength. So the gradient is dz. The gradient is of same strength but in opposite direction. Then what happens? Whatever the magnetic fields which were generated, these extra magnetic fields which were generated, they will get cancelled when I apply a reverse gradient of same strength. So when I apply reverse gradient here, an additional magnetic field of plus 3x will be added. Here plus 2x will be added, here plus x, and here minus x will be added, minus 2x and minus 3x. So all these additional magnetic fields, they cancel each other and you regain the homogeneity in the sample. So the entire sample will have only one magnetic field, that is B naught. Okay. So then you apply a reverse gradient. These magnetization vectors, they start rotating back to the same angle theta to which they have moved during this first gradient. Okay. So all the magnetization vectors will rephase and the signal intensity will be maximum again. So the complete signal intensity will be regained. So let me ask you one thing, or rather let me tell you one thing. This complete rephasing of this magnetization vector, it happens only when you provide this reverse gradient immediately after providing this first gradient. Okay. Suppose if you do not provide this reverse gradient immediately and suppose if you let the sample to be idle for some time delta after this Gz, let us see what happens. The magnetization vector, the sample is at homogeneous magnetic field B naught. You applied a gradient Gz. Now there will be a dephasing of magnetization vectors. Now you are not providing minus Gz, the reverse gradient, but you are letting the sample to be idle for some time. Okay, let us see what happens if I do so. Look at this first example. The magnetization vector is here. Now I gave the gradient strength. It started processing faster or rather slower. When I applied the reverse gradient, then this magnetization vector, it rotated back to the same angle. So I get the maximum intensity of the signal. Okay. So this intensity of the signal is detected by the detector which is present in this direction, in this x direction. Okay. So if this magnetization vector is completely along x, then suppose m is the magnitude of magnetization vector, and since it is completely along x, it is making 0 angle with the x-axis. The component of magnetization vector along x-axis is given by m cos theta. So this theta is 0. So m cos 0 will be m. So the signal intensity will be maximum, which is M. Now, in the second case, see, there is a magnetization vector in this direction. You have applied a gradient. So this magnetization vector, uh, it started precessing faster or slower. Now you are not doing anything. You are letting the sample to be idle for some time delta. Okay. Now during this time, what happens? We know that in the liquid, the molecules are not rigid or fixed. They are under continuous motion, right? They are under continuous translation motion. So during this time delta, the molecule, suppose one molecule was here, suppose this molecule was here. Now during this time delta, is diffused from this position to this position. So when it diffused from one position to other position, now its magnetization vector, to get back to its original position, it should experience the same magnetic field when it was present here, right? So for this complete rephasing of this magnetization vector, this molecule should experience the same magnetic field that it has experienced during the first gradient. But during the first gradient, this molecule was present here, right? But when you provided the delay time, this molecule has diffused through this distance. Now this molecule will not experience the same magnetic field. Therefore, this complete rephasing of this magnetization vector is not possible. So there will be a certain rephasing of the vector, but not complete. Okay. So now, if you look at the component of magnetization vector in this direction, you will see that the component is m cos theta. First say this theta is 45 degree. So the component along x direction is m cos 45. We know that cos 45 is 1 by root 2. So the magnitude of the magnetization vector along this x-axis will be m over root 2. Okay. So there will be a decrease in intensity of the magnetization vector. Okay, since the detector is only detecting the component of the magnetization vector. So we have seen that as the molecule diffused, there was a decrease in intensity. So if the molecule diffuses farther, there will be still more decrease in the intensity. Okay, so this diffusion has something to do with the intensity of the signal. So there were two scientists, uh, Sedgwick and Tanner. What did they do? They established a mathematical relationship between the intensity of the signal and the diffusion coefficient. So they performed this diffusion order spectroscopy at different gradient steps. Okay, and they looked at the intensity of the signal. Okay, so they plotted this gradient versus intensity, and they saw that this data can be fitted to this equation. Okay, so using this Sedgwick-Tanner equation, one can find the diffusion coefficient of a molecule in the in your sample. Okay, so we shall see how do we perform this Dozy experiment step by step. So to perform Dozy experiment, you need to apply an RF pulse, because an RF pulse, it tilts the magnetization from Z axis. Suppose if you are applying a pulse in this direction, this is x axis, this is z axis, this is y axis. Now your magnetization vector is along z axis. If you apply a pulse in direction of x axis, along x axis, it will rotate the magnetization, or it will tilt the magnetization vector from z to y. Okay. So if you apply a 90-degree pulse, it will tilt the magnetization vector from Z to Y. In the next step, what do? You apply a gradient, field gradient. and you dephase the magnetization vector, because all the magnetization vector they start processing with different frequencies, so there will be a dephasing of the magnetization vectors. So let me tell you one important thing. This gradient, strength of the gradient, it is characterized by two parameters, that is, one is g and other parameter is delta. Okay, so this g is nothing but the field strength, magnetic field strength of the gradient, and this delta, it is the duration for which you are applying this field strength. So here this small delta, it represents the duration for which you are applying the field strength, and g is the field strength. Here gamma, it represents the gyromagnetic ratio of a nuclei. Delta is the time delay during which you are allowing the molecules to diffuse through your sample, okay, through your NMR tube. Okay. In the first step, we applied an RF pulse and tilted the magnetization vector. So magnetization vector started processing in presence of V naught. But you have applied, in the next step, you have applied a gradient strength or field gradient pulse for the duration of small delta. Now this magnetization vector, it got dephased. Yeah, it got dephased in the xy plane like this, Now in the third step, you are giving a delay time. That means in this time you are doing nothing, you are just allowing the sample to be idle for some time so that the molecules diffuse to the sample. Okay, in the next step, you apply a reverse gradient to rephase those magnetization vectors. Now, since these molecules have diffused from one place to another place, from one chunk to another chunk, you know that this complete rephasing of this magnetization vector is not possible, right? This rephasing is not possible. So it is said here, due to the translational diffusion of the molecules, the magnetization vector is not completely rephased, which results a decrease in the strength of the signal, nothing but which results a decrease in intensity. So now what do? You perform this Dozy experiment at different field strength and you record the intensity. When you fit this data to Sechel-Tanner equation, you get the value of diffusion coefficient. So in the beginning of this lecture, I told you that this Dozy experiment, it has so many applications in research. So let us see those applications one by one. So first is obvious, that is to determine the mobility of the compounds. You know that we can determine the diffusion coefficient of the molecules. So diffusion coefficient is nothing but the it tells you how fast or how slow your molecule moves in a particular medium. So you can determine the mobility using this Dozy experiment. Okay. So you can study this protein drug interaction. Let us see how do you do this. We know that okay. We know that protein, it is a huge molecule. It's a big molecule when compared to drug. Drug is a very small molecule. Now to know whether this drug is going and binding to this protein, we can do one thing. We know that the diffusion of this drug molecule or is very fast, right? Since this molecule is small and in size, it diffuses faster when compared to this protein molecule. Okay. But when this drug goes and binds to this protein or locks with this protein, the diffusion of this drug molecule, it decreases drastically. So if you see a decrease in the diffusion of the drug molecule in the presence of proteins, that means your drug molecule is going and binding to the protein. Therefore, it can be a potential drug candidate. So this is how you apply Dozy in protein drug interaction. Let us see the next application, identification of individual compounds in the molecule. So if you are given a mixture of compounds, we know that in 1D spectra, you cannot differentiate that this peak corresponds to a particular compound and this peak corresponds to the other compound. That's not possible using 1D spectra, right? So what can you do? You can perform this DOSY experiments, and you know that the peaks which are from the same molecule, they yield same value of this diffusion coefficient, okay? But if you are getting a different value of diffusion coefficient for a peak, that means this peak corresponds to a different molecule, okay? So each molecule has its own diffusion coefficient. So if there is a huge difference in the diffusion coefficient or even a small difference in the diffusion coefficient of those molecules, you can find that your sample is a mixture of molecules, and you can also find the number of molecules present in your sample depending upon how many diffusion coefficient values you get for your sample, okay? So the last application is to study the aggregation of molecules. Suppose you have a monomer, okay? So the diffusion of this monomer is very fast. Now when two molecules of the same uh, type combine and they form dimer, the rate of diffusion will be halved, okay? So the rate of diffusion of this dimer will be half when compared to this monomer. If there is a formation of trimer, then the rate of diffusion will be 1 by third when compared to this monomer. So in this way, step by step, you can study the aggregation or polymerization of the molecules. So I think this was pretty helpful, and I hope you all have understood this topic. So I will come with a new topic in next session. So thank you for now. Thanks for watching.